Right, hello, ladies and gentlemen. This is section 8.2, estimating a population proportion. You'll need your note sheet. You'll need a graphing calculator. In fact, if you have your graphing calculator, you're going to be in great shape. You're going to love some of the shortcuts I give you a little bit later on in this lesson. Okay? All right, first thing we're going to do is we're going to taste the rainbow. Actually, let's not taste the rainbow. I don't want to taste all the flavors of Skittles. I only really like the grape ones, okay? Not that I can't handle eating the other flavors, but grape by far is my favorite. Okay, so first of all, thanks to all the students who brought Skittles in so that we could create one giant sample of them. Okay, you guys are amazing. We couldn't have done this without you. And some may wonder, hey, what is the population proportion of purple Skittles? Okay, so let me write this down here. P is equal to the population proportion of all purple Skittles. Okay, and the reality is that this may be too difficult to find. Okay, in fact, I'm gonna write the rest of this in purple. Okay, and yeah, I don't know. It could be, as some claim, 20%. Okay, because there are 5 flavors, and if they're equally balanced, could be 20%. But I don't know. Okay, it's somewhat unknown, and unless I actually went through and counted, okay, every single Skittle that it was ever made since the early, I want to say 70s or 80s. Okay, um, and separate them into colors and did a count for each one, it's really too difficult to do. Okay. However, I can make a point estimate. Okay, and again, a point estimate is a sample statistic that we can sometimes use to help predict what we believe the true proportion to be. Okay, so here's what we did. We had students, okay, go out, bring bags of Skittles. We put them all together, okay, and made one giant sample of 2,814 Skittles, okay, of which, okay, 636 were purple. Okay, so if I want to make a point estimate to help predict what I believe the population proportion could be, okay, and again, it's a rumor, okay, that maybe it's 0.2, okay, or 1/5, because there are 5 colors, 5 flavors. What I'm going to say is I'm going to make a p hat. There's the proportion, the sample proportion is, in this case, for us, 636 Skittles out of 2,814. Okay, and if you do the math for this and divide it out, you get 0.226. All right, which is a little bit higher than the 0.2 that may be considered as the population proportion. Okay, but based off our results, this is what we got. Okay, interestingly enough, there was a big study done at I think it was called San Juan University, California. They did a similar study. Theirs was actually 0.223, and they had a much higher representation of skills than what we had. So, any case, let's move on. All right, and I'm going to again state that we don't really truly know what P is. Okay, again, maybe a rumor that it is 0.2, but we'll see. But we do know what P hat is, and for us it is 0.226. Okay, there are going to be 3 steps to doing our current work. Okay, and this is step 1. Okay, and that's finding our conditions. Okay, and when you look at this, you think, wow, this looks like a lot of new crazy type of math, but this is actually work that you did in chapter 7. Okay, the first part is the 10% rule. Okay, and if you don't remember the 10% rule, it goes like this: n is less than or equal to 1/10 the big N. Okay, and what is little n? Little n is what we found in our particular sample. 2,814 is less than or equal to 1/10 the big N. And when I think of big N, this is all the Skittles that were ever made. Okay, and so in order for this not to work, basically we're adding another 0 here. Do we believe that we've made at least 28,000 Skittles in a lifetime that it's been, since its inception, okay? And the answer is yes. I've probably eaten 28,000 Skittles myself in my lifetime, okay? So yes, this will be satisfied, all right? Large counts, okay? You remember this as well. This is for normality. By the way, this is for standard deviation, by the way. 10% rule for standard deviation. Okay, because this is satisfied, it means our standard deviation will be valid. Okay, large counts means if we have some satisfied conditions that we will have approximately normal distribution. Amongst a sampling distribution. Okay, so remember that is n times p must be greater than or equal to 10, and n times 1 minus p also must be greater than or equal to 10. All right, so my n is super huge, 2814. Okay, I find, first of all, that these must be hats, okay, that my p hats is more easily represented as a fraction here as opposed to the decimal that I wrote up in this top corner. And you're like, why would you want to make an ugly fraction here and write 636 over 2,814? Well, the big reason is that as I do this work, these will cancel out. Okay, and 636 is definitely bigger than 10. If I do it through the other way, and again, remember you have to do both. Okay, and I'm testing to see if that's bigger than 10. I'll do this on my calculator really quick. 284. Okay, you'll find that you'll get 2178. Okay, and that's much bigger than 10 as well. And what it means is that my sampling distribution, okay, will also be approximately normal. Okay. All right, our last condition is random. Okay, and random means different things to different people. Okay, and I know amongst the people that we had in our class, you went to a store and maybe randomly picked a bag of Skittles. That kind of works, okay? However, what's really truly random, if it's a true SRS, what I'm doing is I'm going to the Skittle factory and I'm closing my eyes and I'm randomly picking from this big drum of Skittles, probably the size of my house, 2,814 Skittles. And that's what truly random is, okay? Is by doing some type of blind pull, okay? Sample, for example, maybe a better word, from again your population of all Skittles, and really that's really hard to do because Skittles have been made for the last 30 or 40 years, maybe longer, and you can't pull from that entire group. Okay, and you can't even really pull from our population that we have. Okay, it's what we currently have on this planet. You can't sample from all the countries. Okay, so I'm going to check this off to say, yeah, you guys probably went to the store and just picked a random bag, and your random is probably just like, hey, this is the first one on top. You didn't like take them all and mix them all up and pick a bag. But for the means of just doing an activity, okay, we're just going to check this off and say, hey, we need this to be satisfied. Okay, and as long as you can do these 3 steps and identify them, okay, and write a little check mark with each one just to say that they are satisfied, okay, then you're good. Okay, and this isn't hard math. It's actually pretty easy. You've done it many times. Okay, you just have to repeat it. So what we learned in chapter 7 repeats in chapter 8. Okay. All right. So once that's done, we will go on to step 2, and actually to do the math. Okay, and it involves a formula that I'm going to highlight right here that you have used in the past. Okay, now I'm asking for a 90% confidence interval. Okay, and what may be a little comfortable to you is that we haven't done a 90% confidence interval. We did a 68, we did a 95, we did a 99, and those 3 were approximately very close to 1, 2, and 3 standard deviations away. And that is what I put under this item symbolized with a Z. Okay, and here's what we're going to do. We're going to be a little bit more specific now. Okay, when we said, for example, that I'm going to write this down, 2 standard deviations was 95%, that was pretty close. Okay, that was an approximation, and that's okay for our empirical rule. Okay, however, we're going to be a little bit more exact since this is just an approximation. Let me adjust that. Okay, 95% is really what you see off to the right, kind of over here. It's not actually 2, it's actually 1.96. Okay, so here's what I'm going to share. In 8.2, okay, and in 8.3, if you're ever asked for a 95% confidence interval, and we're doing proportions, right, then you're going to have to do a z value, okay, a critical value, okay, that is 1.96 and not 2. Okay, 2 is kind of like outdone. Okay, we're not using that anymore. Similarly, okay, 99% we said was 3. Okay, and if you can remember from my last lesson, I didn't really say 99 was really 3. I said that 99.7% was 3. And that's true. Okay, this is about 3. Okay, but if I just want to use 99, I'm going to replace that with a 3. Sorry, replace that 3 with a 2.576. Okay, and then a 90, of course, will be 1.645. That's a new one. Okay, I'm going to keep that out and handy for you so that as we work through these problems, they're available to you. Okay, you'll find that as you work through 8.2 problems, okay, you're going to use these 3 fairly exclusively. Okay, and in time you'll kind of have them memorized. Okay, but I will give you a sheet for it on your test and on your final. Okay, that will have these available to you in case you don't have them remembered. Okay, or memorized. So how do I do this? Very similar to before. Your p hat from, again, the other side was 636 and over 2,814. Okay, plus or minus. Now, in this case, I'm using 90%. And so the z, or the critical value that corresponds with 90%, is 1.645. Okay, times the standard deviation. Okay, and so I'm going to put this in as it should be. It's our p hat, 636 over 2814. Okay, times 1 minus 636 all over 2814. Okay, all over 2814. Okay, and remember that this fraction is still underneath the root bar. Okay, so to make this a little easier, I'm going to say this is 0.226 plus or minus 1.645. And this, I'm just going to say, is an ugly monster to put in your calculator. And I'm just going to share that I did already do this. This is going to give you 0.008 as you round that. Okay. And if I take it a step further, okay, I'm going to say 0.226 plus or minus. Now, that 0.008 is rounded. And from my calculator, I'm going to take that and multiply it by 1.645. Okay, and that will give me 0.01296. Okay, so 0.01296, basically 0.013. Okay, and then we will add these and subtract this. Error, remember this part in the back is called error, just to remind you, to the 0.226. Okay, so I like to use my calculator just to make sure I don't make a silly mistake, because that happens with the best of us. This will give me 0.239 as an upper boundary. Okay, and then my lower boundary is, I'm going to put that 0.01296 in as well. Subtract those out, 0.213. Okay, and that is the calculation portion for our work. No different really from what you did in 8.1. This part here in the front is the same. This part here in the back is the same. The only difference is your z. I'm not using numbers 1, 2, and 3. I'm using actually these three. I'm kind of pointing to them right now in my table. It's either the 90, the 95, or the 99%, these three values for your Z, okay? And notice I title it that way with the Z right there. Some may ask, is there a different percentage that may not appear in this table? Like, is there a 96% or a 98%? And the answer is yes, okay? However, for now, just worry about those three, okay? Those are the ones that appear most often. And when we get to the newer ones, I'll show you a different method to get those, okay? All right, so step 2 is done. Let's move on to step 3. And step 3 you've done before too. Okay, we're just gonna make a sentence for this, all right? And if I attach the sentence to the very last slide of this, I'm gonna see if you still remember it, okay? And I'm using a different percentage, I'm using 90%. We are 90% confident the interval, okay, from 0.213 to 239 captures the true. Now let's think about it. We talk about means or proportions. Well, hey, let's look at our formula. There's a bunch of p hats here, so yeah, this is proportion of purple, or you can say grape, Skittles, I don't know, and I think that's it. Okay, captured your proportion of purple Skittles. Okay, and so we're 90% sure that, yeah, the true population proportion, which again, we don't really quite know, we have speculation, okay, is between 0.213 and 0.239. Okay, now the original claim, okay, that may or may not be true, is that they're equally balanced, which means that's 0.2. Would we trust that based off our sample? Okay, and the answer is no. We probably wouldn't trust that they were equally divided and that the true proportion is 0.2 because 0.2 does not fall within this confidence interval. Okay, 0.2 is on the outside, it's on the lower portion of it, and because of that, it doesn't make it believable that they are divided evenly. Okay. All right. Let's proceed. Okay. So here, another moment where data has been done for us. Okay. It says, as a retirement gig, Mr. Castillo chooses to supplement his income by making loaded dice and using them on a craps table in Las Vegas. Players are extremely successful when the sum of 7 occurs on the first roll. Mr. Castillo tests his loaded dice by randomly rolling 300 times and recording the sum after each roll. He found that the dice produced the sum of 7 on 72 occasions. Okay, so let's make a p hat here for our sample. Again, p is equal to the proportion. And you can say the true proportion or the population proportion. You could write both, sound great actually. True population proportion of the sum of 7s when 2 dice are rolled. Okay, now I can figure out mathematically what that should be, just in theory. But remember, he has loaded dice, okay? These are ones that are adjusted in some way where it may not be equal to the true proportion, okay? In fact, if you think about fair dice, okay, that's not quite what these are, okay? This is what we're talking about. We're talking about Mr. Castillo's true population portion of the sum of 7 when 2 dice are rolled. And again, these are Castillo's dice. Okay, so I want to know what his population average is. Okay, I know typically the probability of rolling a sum of 7. Well, to roll a 7 on fair dice, and I'll write this off to the side, You can get a 1 and a 6, a 2 and a 5, a 5 and a 2, a 6 and a 1, a 3 and a 4, and a 4 and a 3. So there are 6 out of 36 ways to roll a pair of dice and get a sum of 7, which is 1/6. I'll write that down here. So that's if they're fair. But again, you don't know if these are fair. They're made in a way where they're not fair. Okay, and so in the end, when I think about this P, I don't know what his true proportion of times that he gets a 7 is. Okay, but let's do a point estimate. So for a P hats, he rolled a 7, 72 out of 300 times. Okay. And you can divide those out if you want. That does give you 0.24. Okay, it was actually quite often. Okay, so what are we going to do with this? It says test the conditions and then create a 95% confidence interval. Okay, so again, there are 3 steps to answering this question. Step 1 are the conditions, and the first one is the 10% rule. Okay, and so remember, this is little n is less than or equal to 1/10 the big N. Your little n is 300. Okay, your big N are all dice rolls. And what we're kind of asking is, can you roll a dice or a pair of dice more than 3,000 times? You certainly can. Okay, and if you do that, you'll satisfy this 10% condition for standard deviation. Okay. The next one is the large counts for normality. Okay, so I will do n times p and n times 1 minus p. Okay, people will ask, do you have to write the formula down? And the answer is no. You can just plug the numbers in and write it down. Okay, so again, our n is 300. Okay, our p was 75 over 300. Again, I like to write the fractions because they're easy to cancel out. And you'll get 75 is greater than or equal to 10. And same thing for the next one, okay? 300 times 1 minus p, which is 225 over 300. I just did that math quickly in my head. And the answer is 225. That is also bigger than or equal to 10. So our large counts for normality is also satisfied. Okay, so our sampling distribution will be approximately normal. Okay, the last one, okay, it wasn't random. Okay, did he have random rolls? Well, gosh, we'll assume that all your rolls are independent. Okay, and while you can roll dice forever, you know, I think it's probably pretty trusting that his dice were fairly rolled. Okay, though I don't know if you could say they're completely random, because if you took all dice rolls, you'd have to pick and choose certain dice rolls from pretty much the infinite population of them. But again, because each outcome is independent, we don't feel there's any trickery in terms of how you rolled them. Saying that the dice are rolled fairly is good enough for me. Okay, and so I'll say yes, they're random. Okay, so these 3 conditions were satisfied. Okay, and it says use your confidence interval. Use your information to create a 95% confidence interval. Okay, so again, using the formula from before, which is p hat plus or minus your z times p hat times 1 minus p hat all over n. And I'm going to just write the same things as I did before. It was 0.226. Oh, sorry, that's not right. 0.24. Let me erase that. .24. Okay, plus or minus the z. Okay, now let's think about z. Z was for 95%. I'm going to circle this in the problem, which means I'm not going to use the 1.645 like I did on the previous slide. For 95%, notice I'm pointing to this table over here, this big circle. 1.645 was for 90%. 95% is 1.96, which again was really close to that 2. So I'm going to say, can I use 2? For now, let's practice using 1.96. Okay. And then in here, I'll use my new p, which is 0.24. And if you want to write the fraction instead, like 72 over 300, that's fine. Or the reduced fraction for that, that would also be okay. Okay, 1 minus 0.24 is 0.76, and again, this is over 300. All right, so if I do the standard deviation, okay, you would get, and I'll do this quickly for you, 0.024657. Okay, 0.024657. Okay, and then after that, what we'll do is we'll take that and multiply it by 1.96, not 2, and it gives you 0.048. And if you want to be a little bit more picky, you can say 3. Okay, and if you want to do another number, you can say 3 again. Okay, and then we will add this and subtract this to this value of 0.24. Okay, so when I do the lower version of that, I get 0.19167. Okay, and the upper will be 0.28833. Okay, and so again, step 1 is the conditions, 1. Step 2 is doing the math, good. Step 3 is writing your sentence, okay? And they're all worth equal weights when it comes to doing a problem like this on your AP test, okay? So your conditions here, which is just this moment in the beginning to say that, yes, this is appropriate for you to use this test, okay, must be done. Okay, and if you don't do that, there's heavy penalties for that. Okay, most people are okay doing part 2. They understand that, hey, this is kind of the meat or the math of your work. Okay, but the last part is also important, and that's the ability to describe what's going on here. All right, and here's what we're going to say. We will say that we are 95% confidence. Okay, the interval from 0.19167 to 0.28833 captures, okay, the true population proportion of dice rolls. Okay, and these are Castillo's dice rolls. Okay, maybe I'll put that in parentheses just to emphasize. Okay, because he has special dice here. True proportion of dice rolls that have a sum of 7. Okay. Very good. We are 95% confident the interval from 0.19167 to 0.28833 captures the true population proportion of dice rolls, Castillo's dice rolls, that have a sum of 7. Okay, so that's the percentage of time we get a 7. Okay, so same type of work. You're used to doing parts 2 and 3. You're used to doing parts 1, but again, you did that last chapter. Okay, now you're just adding this first piece to it. And if you ever have a wonder, will you ever use a word besides proportion in answering this question? I'm kind of lightly circling this near my my video here. And no, in this chapter, in this section 8.2, we're only dealing with proportions. Okay. All right. Last thing says using the interval and considering the probability of rolling a 7 with fair dice, does Mr. Castillo's dice provide an advantage? Okay, well, we found out earlier that the probability of rolling a fair dice, I'm up in the top left-hand corner here, is 1/6. Okay, 1/6 is what a fair dice is, and that's about 0.16666 forever. Okay, 7. All right, so what I want to know is, are these good fake dice? Okay, and the answer is yes, they are. Okay, these are dice that will provide a stronger advantage. They will roll 7s more than a typical dice. Okay, and the reason why I know that is because we are 95% sure that Castillo's dice will have a sum of 7, somewhere between 19.167% and 28.833%. Okay, and notice that that 1/6 or 0.1666667 is not within the interval. Okay, and so since it's not within the interval, it means that a fair dice is not included within what Castillo's pool of dice would be. All right, and so yeah, Castillo's dice roll 7s more likely or more often than a traditional dice. Okay. All right. Now here's the part you're gonna like. It doesn't mean to be redundant here. I'm giving you an opportunity to replace work that you would do for step 2, and you can do this all in your calculator with your TI-84. Okay. So step 1 still has to be the same, but step 2, okay, you can use a calculator for. Okay. And so here's what you would have to do. You can have your calculator out, and you can pause this anytime you need to if you feel like I'm going too fast. You're going to hit stat. Okay, and then you're going to scroll over to tests. Okay, so notice I have tests. It's the last column. I'm hoping my TV, like my video screen, doesn't cover it. Sometimes it does on accident, but yeah, you got to go to tests, and then so stat. Then you go to test, and then you have to go to A. Okay, A means you got to scroll down past all the numbers until you finally get letters, and it's called one prop Z interval. Okay, and if you proceed and hit that, okay, you're going to plug in Castillo's information. Okay, what did Castillo do? Well, right here, I'm going to darken this. Okay, his X value, which is the numerator, is 72. His denominator is 300. And your confidence level, you're going to have to maybe change this to 0.95. Okay, and once you input 72 and 300, you'll hit calculate. Okay, but before I do that, just to remind you, these numbers X and N in your calculator, they have to be whole numbers. Okay, and even almost say they have to be natural numbers. I don't think you can have a 0 in for your X. Okay, so there are usually, I don't think you're allowed to have decimals in those spots. Okay, so make sure that you have nice whole numbers in those. Otherwise, you're going to get error. Okay, go along and hit calculate after that. And when you do, you'll notice the interval they gave you. And that is the same answer that I had on my previous screen. Okay, so you probably have that written down on your paper. Okay, are you allowed to use this step on your calculator to replace step 2? You can. Okay, step 1, you still have to do the conditions. Write this off to the side. Okay, you have to have all 3, the 10% rule, the large counts. Okay, and then you have to talk about random. Okay, step 2, you can do all in your TI-84. That's all you have to write, TI-84, and then do the command. We'll just say that we did, it was 1 proportion z-test. Okay, so just write the command that you did, and then give me an answer. Okay, but you have to write this. Okay, you can't just skip this step and say, hey, I did it in my calculator. Tell me what you did to replace the shortcuts, okay, from what appears in this kind of ugly box. Okay, so I'm saving you a ton of time by not having to do this. And again, this is a much better alternative. Okay, but you have to write TI-84, 1 proportion z-test, and then write the answer. Okay, and then third, of course, you have to write the sentence. Okay, so the only part that this helps you with is 2. Some people say, which is the better way? I like doing the calculator way because I know I'm going to get a nice answer that's doesn't possibly be a result of maybe a small miscalculation from one of these ugly equations. Okay, so if you think about this equation over here, this is kind of messy. Okay, and I would much rather just plug in 2 numbers and then a confidence interval for my calculator and get it the same answer that I had before. Okay, don't mean to confuse with all that. So, all right, so yeah, definitely awesome way to do this. Okay, all right, 3 steps. Always show me those 3. Always show me them. Okay. All right. Here's the last thing. It says, suppose you want to estimate the proportion of students at Perry High School who have a tattoo with 99% confidence. Okay. And a margin of error of no more than 10% or 0.10. Determine the number of students that you need for the survey to estimate P within 0.10 with 99% confidence. Okay. So let's think again about the formula. Okay, and let's think about what error is. Error is, notice I'm going to write here, I'm circling this out, boxing it actually, margin of error, that's this guy. And I'm just going to abbreviate that with an ME. Okay, margin of error. And it can't be bigger than 10%. Okay, so my margin of error, okay, cannot be bigger than 10%. Okay, so that's this piece. All right, I'm just going to replace this back of the formula. I'm not going to use the plus minus, it's just the z and the square root feature, where the margin of error is. Okay, so now I know what z is because I have 99%. Okay, then I'm going to use its representation for a critical value. 99% confidence interval has a value of 2.576. That's in your table. You used 90% one time. That was 1.645. You used 95%. That was on the last problem. That was 1.96. And 99 is 2.576. Okay. So let me write that. My z okay, 2.576, okay? And they don't really give us any other information, okay? They say determine the number of students. Now, let's think about that for a second. If I say number of students, does that represent a p hat or does that represent an n? Okay, and since it is a number of students, that means that yes, my n is going to be on the bottom, and that's what I'm finding. Okay. Now, what is p hat? They don't tell us what p hat is. Okay, and if they don't tell you, the default, okay, for p hats is 0.5. Okay, so I'll say 0.5, 1 minus 0.5. And here's what's going to happen. I'm going to give you a test question that has this, and I guarantee you one of the 30 people in my class will walk up with their test, and you'll have this part here completely filled out perfectly, but you're like, Rothery, Mr. Rothery, I don't know what my P is. It doesn't show me, okay? And I'll say, you're right, it doesn't give it to you. And you'll look at me confused, and you're like, what do I put in there? And I'm not going to tell you, okay? In fact, I may, I would say embarrass you in front of the class, but I don't want to do that. But I guarantee you there's always one student who will come up to me and say, hey, I don't know what p hat is. And I'll say, we talked about it. There is a default. I don't even know if I'll tell you there's a default, but you have to know it's 0.5, okay? And from there, we'll just plug this in and work it out. Okay, so this is 0.5 here, this is 0.5 here. Okay, and we're gonna solve for n. Okay, so I can divide both sides by 2.576. Now notice, I'm gonna call this 0.5 squared if you don't mind. I'm not going to divide this out. I'm just gonna say 10 over 2.576. Okay, and then I can split these up if I want. Okay, and then from there, I'm going to cross multiply. Now I'm going to do a shortcut. I know that 0.5 squared, all square rooted, the square and the square root will cancel out. Okay, so as you cross multiply, you get 10 times the square root of n, and then this will give you just 0.5 times 2.576. Okay, so again, 0.5 squared, all square root is just 0.5. And I've got 2 steps to get n by itself. I'm going to divide by 10. Okay, and then what I'm going to have to do is square both sides. Okay, and let me do this math first before I square both sides. I got 0.5 times 2.576. Okay, divided by 10. Gives me something a little bit smaller than I was hoping for. Let me make sure we did this right. 5. Oh, pardon me. Found my error. Hopefully you saw it. I'm going to put this in red so you can see it and explain why this is a big mistake. This is not 10. This is 0.10. Forgive me. Okay, so that will change things, certainly. Okay, so 0.5 times 2.576 divided by 0.10 gives me 12.88. Okay, and then to get n by itself, we'll square both sides. And then we'll be done. So I'll keep the 12.88 in my calculator, I'll square it, and I'll get 165.89. Okay, and here's the deal with n. Okay, this will always happen while I write it this way. Okay, when you have your n, you're always going to round up. Okay, so your 165 will actually round to 166. Okay, so always round up no matter what. Okay, even if you had something like this, I'm going to write this a little bit above. If you had 165.23, normally we'd say, hey, the decimal of the 2 would mean that we would round this down. But because this is an error in the bottom here, okay, this value is going to be in the bottom here. The bigger this number is on the bottom, the smaller this will be. And the smaller that'll be will guarantee that it'll fit a value lower than 0.10. Okay, if we make this smaller than what it should be, okay, then it makes this actually larger, and it actually will be bigger than the 0.10. Okay, so even if this is a kind of a crazy example, it doesn't follow the rules that we typically follow in math class, but 165.23, if that was the answer, okay, you would still make that 166. Okay, so that's a little arrow. Okay, so always round up. Okay, because again, we're talking about people, okay? We don't want 1/3 of a person or 1/8 of a person or 0.23 of a person. You always round up no matter what when you're solving for n, okay? All right, thank you so much for your attention. I hope this all made sense. I hope you like talking about Skittles because I did. And again, the purple ones are the best, okay? Just a reminder of the definitions for a confidence interval and a confidence level. They may ask you some of those in the review, okay? So have those handy if you need it. And there's your assignments, okay? Again, remember, oftentimes they ask for point estimates and errors and values for Z, okay, your critical values in the beginning problems, and then you'll probably have to do more confidence intervals as you move on. Remember that you have 3 steps: the conditions, okay, and there's 3 small conditions: 10% rule, the large counts, okay, for normality, which is n times p, n times 1 minus p is greater than 10, and random. So a lot of these questions will really just say, hey, are your conditions satisfied? And if that's the case, you just do step 1 and you're done, okay? And then, of course, you gotta do the calculation. Use your calculator if you want, the shortcut method, that's fine. And then always write for me a good sentence as you practiced, okay? All right, I hope you have a good day. And if you have any questions, you let me know. We'll talk to you soon.